Hello, Amiga coders. This is Photon ScoopX, and it's time again for another installation in our series about hardware programming for Amiga. Well, we finished off by exporting our logo from that we had drawn in Deluxe Paint. And what you can see on the screen is our working directory. We did export two things. We exported the bitmap format or bitmap converted logo, and we noted the width, height and depth of the logo, which will come in very handy today. And of course, when you do this, when you make all your Amiga demos for the future, then if you have to leave a project and come back to it 2 months later, you will have this information there, and there will be no doubt. We also exported the palette in the form of a copper list. I think we ended last session by putting the palette in the copper list, yes. So what's left now is to include this binary format, bitmap format or raw format logo. And the difference between include binary and include is of course that include works like include in all the other languages. That is, whatever file you include is included as text, as if you had pasted that text in this text editor. Whereas include binary takes whatever address you have assembled to after the end of this copper list. That address gets this symbol name, and whatever's in this file is loaded starting at that address in memory. And I talk so much so that I have to look at what the file name was. If you wish, you can do like this in ASM School. I'm sorry, in ASM 1. There's a directory. If you press Control Escape, you can keep the information down here while simultaneously editing the text, so that you can just copy the file name text just like that. And I like to put end labels after my binaries and includes. That way I can get a sort of a rough profiling of memory spent. In our case, we'll probably not run out of memory for this little demo that we're working on, but it's good practice. So what happens if we run this? Let's see where we were. Well, nothing much. The palette has changed so that when we set the palette at the top of the screen, just below the light blue 1 pixel top border, it sets the correct background color, a medium gray. And we have our random data, which sits in our screen buffer, and we have our little sprite that we defined once upon a time. So while we know that this is in memory and we can have a look at it, as you can see, there are very many zeros, which is why IFF files, who do run length encoding compression on all these zeros and FFs in the bitmap converted image data, become so much smaller than the real thing. However, there's no real-time decompressor in Denise, so, and also it's more useful for plotting and processing if we don't have to decrunch a screen buffer before we can set or clear a pixel in it. Don't you agree? So this is it. These bytes are just 8 pixels at a time. First in the first bit plane, and then comes the next line in the next bit plane, and then comes the next line in the next bit plane. and then comes the next line in the picture, starting again at bitplane number 1. This is called interleaving. You can also have the other way, as I showed you in the IFF converter. You can convert it to a normal raw format, in which case you get sort of strange looking outlines of the logo. One big bitplane, all the lines in a bitplane. In bitplane 1 first, and then the next bitplane, and then the next bitplane. So that you have sort of, if you can imagine this picture that I tried to paint in a previous tutorial, that bitplanes are like layers. You get the layers one after another in memory, but in this case, in the case of interleaved bitmaps, we sort of slice the entire picture into pixel lines, and you get the layer, the first line layer, and then the first line layer bitplane 2, then the first line bitplane layer bitplane 3, and then you get the second line on the screen, so that you have 1 pixel high layers, just like that. It works sort of like, well, they're interleaved, they're sort of weaved. I will show you this visually right now. Now to show the bitmap, I'm sorry, the logo bitmap on the screen, well, currently we're displaying the screen buffer, which is up here. We've defined a width, height, and the bitplane size for the screen, and we've put it somewhere high in memory, which is available. We know that. And down here at the bitplane pointers, we have set the just the one bitplane pointer to point at this 1 bitplane screen buffer. Now it's different. Now we have 3 bitplanes, so we need to set 3 bitplane pointers, and we need to point them to the logo. I'm going to just change this to show you the logo in memory. As you can see, from the top to about halfway down the screen, you see the logo. That's actually the interleaved, all the 3 bitplanes of the logo interleaved 1 scan line by 1 scan line. And the width of the screen is incorrect, so that you get several Y characters and several K characters and several S characters to spell out SKY, sky, that we drew the logo. So this is a visual representation of the bitplane data we just looked at in the monitor, displayed by Denise. So, what's wrong with this picture? Well, we need 3 bitplanes to start off with, and that's what we set down here, because after all, we set all these 8 colors in vain when only these first one, the background color, medium gray, and this color is used. So let's set 3 bitplanes and see what happens. Well, there you saw a rogue, well, it's often called a rogue copper, but it's actually uninitialized bitplane pointers. So what happens is that Denise reads a screen full of bitplane data, just as it does for bitplane 1, which has its pointer set each frame, but the other ones, they're increased by 1 screen full each frame, and so Denise rattles through memory and displays, well, you could see the the CLI screen and some assembler text flashing by there. And so this leaves the bitplane pointers, and they lie one after another in the custom chip register area, like this. And of course now they're all initialized, so that we should get rid of the flickering by of screenfuls of data. But the color changed because now we have set all the 1 bits in bitplane 1 are active in all 3-bit planes, so that wherever there's a 1 bit in the first bit plane, you get color binary 111, which is 7. So you get the highest color in the 8-color palette, which is red. No mystery there. However, now we want to correct some things. I don't know if I should correct the display window and width of the screen first, or what to do, but tell you what, let's be good boys, and I'm starting to sound like Neil Tennant with an American accent. I'm not supposed to. Just like we defined the width, height, and bitlane size and some other neato stuff for our other screen, we can do it for this little graphic. After all, the screen buffer is just a graphic as well. It's a 1-bit plane, quote-unquote logo, that is very much larger, 320 by 256. So let's check this out. I think I will. Well, what happens is that we should define a logo width and a logo height to start with. I'm not sure the logo height is necessary, but why not be good boys? And it was 178. However, bitplane data is stored a word at a time because of the way the DMA engine works in the Amiga custom chips, so that all graphics have to be rounded upward to the nearest multiple of 16 in pixels. One word is 16 bits, so that when we have this width 178 and divided by 16, we get 11 words. However, unless 11 times 16 is exactly 178, we need to increase the width by 1 word. As you can see, we're sticking out into the last, the rightmost word by 2 pixels, which means we have to have 12 words, so the width is 192. Logo height was already forgotten, 67. And we can do some other things, but I think I will show you now the one thing you need to change. The problem we had was that these letters seem to repeat and wrap around because of the width being much smaller for the logo. What happens is that Denise reads right now 20 words per scan line, which makes up for the 320 width of the screen, which means it reads slightly more than 1 line of the logo before it reaches the right edge of the screen. So we need to just make the screen size less wide. We do this in 2 ways. We change the DMA fetch, start and stop, and we change the display window. We'll start with the DMA fetch, start and stop. So we need to find out how much we should shrink how much we should shrink the screen horizontally. In other words, how much we should move the DMA fetch start rightward into the screen, and how much we should move the right edge also into the screen leftwards. In these values, if we increase this by 1, we've changed the width by 2 pixels. That means we must have our results from calculation. So we'll start by setting a logo margin and we do this margin by taking the difference between a normal DDF start and stop, which is 320 widescreen, minus the logo width, I'm sorry, and divide it by 2. It's simply the difference in width divided by 2. That's the margin on either side. So what do we do with this? Well, we add it to the DMA start and stop. I'm sorry, the DMA start. And we subtract it from the DMA stop. The exact terms for these are DDF start and DDF stop. Now, if we added the logo margin, sorry, if we added this straight up, we would get a much too narrow screen. As I said, each value here counts as 2 pixels. The DMA fetch only has a precision of 2 pixels, 2 low-res pixels. And so we need to divide this margin that we calculated by 2. And this should somehow make our logo better. As you can see, it's now legible. However, we've initialized all the bitplane pointers to the same position in memory, and we ask it to display the logo as one big 1-bitplane logo, which is why it's stretched 3 times. We need to make it interleaved, and to do this we need to calculate the what I call the byte width of an interleaved line in the logo and the logo bitplane size. And that's the same as this bitplane size. However, this screen buffer is not interleaved. We may opt to do this later on if we add bitplanes to it, but for now I'll just add some fancy comments here. There we go. And to do this, you calculate the number of bytes per bitplane. Well, that'll be twice the amount of words. We knew that the number of words for each bitplane was 12. So logically, the bitplane size for the logo should be 24 if it's measured in bytes, which is what we're interested in. So we need to calculate this, and we simply take the logo width divided by 8, because 1 byte is 8 pixels in a bitplane. From this we can easily calculate the logo byte width, which we need later on for the modulo, which I'm going to touch on. We're going to call this logo bwidth. Better be consistent. There we go. And this is exactly the logo bitplane size times the number of bitplanes. So it's very easy. Well, nothing has changed, of course. I'm going to save this now, so that if something happens, I won't have to start over. Okay, so we have these values that we can add. We can add this to the bitplane pointers. As I said, when we run this, all the bitplane pointers are initialized to the very first line of the logo. We want the second bitplane pointer to be initialized to the second line, the second bitplane of the logo, and the third line, the third bitplane pointer to be initialized to the the start of the third bitplane of the logo. And then we will use modulo to skip 3 lines. Skip to every 3 lines, so that this this rasterized effect disappears and the logo appears 1/3 as high as it is now. And this is how you do it. We're going to put parentheses around this already has the parentheses, the low half of the bitplane pointer address. And this is actually a chore to do. So I might actually show you how to do this, as they call it now, programmatically. I'll show you how to do this with code. We're going to initialize the bitplane pointers with a small initialization loop. And this is how you do that. We can do this at any time. However, we might as well do it in the hardware init that we had here that filled the screen buffer. We need it to be done by the time we start the copper, so why not put it just before setting the copper pointer? It's no good pointing it to a copper that doesn't have any doesn't have initialized bitplane pointers. So what we'll do is I'm going to put this here, and the address that we're going to poke, if you saw that before, it was top BPLP. And we're somehow going to modify this value and poke the lower and upper halves of this address into the copper and increasing them by 1 bitplane as we go. And we're going to make a loop that repeats 3 times. And we do this by putting 3 minus 1 in the 0 and call this bitplane loop, perhaps. And this is the shell of our loop, and inside the loop we're going to put some instructions. We know that we have the first line of the logo, a pointer to the first line of the logo in address register 0 to start off with, and we know that we are pointing to copy BPLP. Let's double check that. If we move anything into this pointer, into A1, then we overwrite this move instruction. We want to put it at an offset of 2 from that, and the lower half we want to put that at an offset at 6 from that, so that we skip the first word and poke something, and then skip another word and poke something. So let's go ahead with that. We're going to take the value in A0, the entire long word, put it in a work register that is free, and it is. We used D3 through D5 for some counters, if you remember. And we're going to swap down the high word of this address and put it, and carefully now put that word in at an offset of 2 from the current poke pointer. We may as well pointer to first bitplane of logo, and this is where to poke the bitplane pointer words. It's a good exercise, so that we can get rid of all those shift instructions and stuff that we had, and fixed addresses that we had in the copper list. It's ugly. We've taken care of the high word. We swap that down again and put the low word at an offset of 6. Now we need to both increase the bitplane pointer to the next bitplane, which will be logo BPL bytes higher than this in memory, and we need to increase this to the next 2 bitplane pointer words in the corpora list. So why not look at that? If we here's a shortcut to not have if we type this, we get this monitor screen. If you just want to display it at the command line prompt, you put an ampersand, an alpha sign, whatever, an @ sign before it. As you can see, they're all initialized to point to the start of the chip memory. High word 0, low word 0. Combined, these two give the first bitplane pointer, and it points to address 0 in memory, which contains libraries and stuff, and not the graphics data that we want to display. All right. So we see at our bitplane pointer was pointing to here, and we need to move it to get it to the bitplane pointer words for bitplane 2. We need to skip 1, we need to skip 2, 4, 6, 8 bytes. So let's do that. The quickest way, here's a new command, is to do add q number 8 to the destination pointer where we're poking. We can comment this if we really like. And we need to add a bitplane, and then of course if we check the value of logo BPL, it's higher than 8, and that means we can't use the add quick command. Instead we need to add logo BPL to A0, and we're done. The next time it repeats, it will do the same thing again. Put the source pointer or logo pointer into D1, swap down the high word, poke it, swap down the low word, poke it, and move on. And it will do this 3 times. There's an alternative to this instruction, which I prefer, and it looks like this, and it takes the A0 register, uses a so-called addressing mode, just like we put an offset here to temporarily increase the A1 pointer to some higher address. We do it here, but since we are loading an effective address into A0, we make this new address permanent. So this is the same as adding logo BPL immediate value to A0. So we're done. Let's check it out. I'll just update the source first. It's not that I don't have faith in my skill. However, as the famous t-shirt slogan goes, shit happens. By the way, well, what you see now is more than one color on the screen, which means that the logo bitplane pointers are indeed pointing at different locations in memory. However, each of them repeats. Well, we simply need to set the modulo for each. We need to set the modulo to accommodate for the interleaved mode. Okay, by the way, what you see below the logo here is just random data in memory that happened to be there before I started. Well, I should reveal that it was blank, but I wanted to talk about it, so I filled it with hexadecimal AA. Just to have something to talk about. Well, of course, we haven't. Well, we've set the screen height to 256 pixels, which means that it will continue to display whatever is in memory after where we ink binned the logo, which in this case is this this pattern. So that's just to demonstrate how it works. You just point the bitplane pointers to some place in memory, and Denise faithfully just blurts out whatever's there until you say stop, which we will do with display window stop register. Alright, so the modulo, well, what's that for? Well, basically it is for skipping bytes in memory so that you can have these interleaved bitmaps. And it's right here. We've set it to 0, 0 already. And they consist of 2 registers, one for odd bitplanes and one for even bitplanes. And we need to set both, since we use both odd and even bitplanes. We use bitplane 1, 2, and 3. We need to set both. In dual playfield mode, you can have different modulos for the frontmost and backmost playfield. But that's for another tutorial, I think. Alright, so what should it be? Well, it should be exactly this. And this is the formula I use in all my sources because it's very simple to visualize and think about, and we've already calculated the value. Since the bitplanes are this, since each line of a bitplane is this big, 24 bytes, then it follows that the logo byte width for a logo with 3 bitplanes is 3 times as much. What you do with the modulo is, well, I can explain what happens. There we go. We have some issues still with the palette, it seems. We'll fix those later. Either way, what happens when Denise reads the bitmap data in memory is it reads as many bytes as many words, I should say, as specified by DDF start and DDF stop that we adjusted earlier. Then it adds the modulo value to all the odd and even bitplane pointers to point to the next line in your graphic, or screen buffer for that matter. So that if the modulo is 0, it just continues on in memory without adding anything. Well, adding 0. But since we adjusted the modulo registers now, it can correctly find the next line. Well, the source of the error was easy enough to find. I actually overwrite one of these palette colors from the logo further down in the source. And here's the culprit. We set color 1 to something. Let's have a look, see if it sets something else. No. Well, there you have it. So what else should I talk about? Well, you may have noticed that the sprite is behaving differently. Well, here's the thing with OCS. When you change the DDF start value, then you affect the left edge of when sprites are starting to be displayed, regardless of the display window. However, on the right edge, as you can see, the DDF stop does not do the same thing. So this has been exploited in various demos with some sprite logos at the right edge here. So, and that's helpful because you can then shrink the screen, which means that if you have many bitplanes on, you will save some DMA time for the blitter, while still filling the screen, so to speak. So that's it. What should we do to our little demo here? Well, first of all, we should remove those stripes below the logo, don't you think? I may want to do something with the screen buffer later on, instead of filling it with random data. So why not use our little loop there and put some bitplane pointers lower down and attempt to have a full width screen at the lower part of the display. Also, I need to move the logo down a little bit, I think, which we can do with the display window vertical start. And it of course looks strange with that sprite, so that I will not have that sprite across the logo, but rather across the screen buffer below it. And I will move the raster bar to do something nice around the logo there. Okay, so first things first, let's move the logo slightly more to the middle of the screen vertically. And we do this by adjusting these values. Let's just try some. And we need to adjust the display window perhaps. This is now set for a 320 pixel wide display. We don't need to change that unless we need to actively crop the area horizontally to the left and right of the logo, but I don't think we need to do that. Otherwise, the way you would do it would be to, well, I can show you real quick. You would add the logo margin here, and you would subtract the logo margin here, with a caveat that this value, which is actually hex 1C1, that is higher than 256, must not fall below 256. But in our case, it's pretty safe. And if we do that, we should be able to see, let's restore this to where it was, should be able to see the sprite being cut off there. Yeah. So that explains the display window values there. We don't need to do that. We need to move that down, and we need to add something to this stop value. This should be hex 4C plus something, this byte. And we can do that by well, the simplest way, I guess, would be to convert this to bytes, so that you would get this word would be 0,80, and you would put a comma and a $sign here to make the two words become 4 bytes. And similarly here, you would go like this and like this. And then all you would have to do here would be to add logo height. And that would cut off. Now we've moved the logo down by hex 20 bytes by 32 pixels. And we've cropped the lower portion of the bitmap data by using the display window vertical stop register. So it's looking distinctly cleaner now. However, we need to do something about the screen buffer so that on this line, which we can calculate, on this raster line we need to set new bitplane pointers and set the number of bitplanes to 1, and some other things. So let's do that. And we do that by introducing a weight at the very... Well, we have to be careful here. I think we'll have to move the raster line. We have to set the bounds of the raster line to above hex 8F, so that we can put the weight here, so that the movement of the raster line, which we're doing with the copper, doesn't interfere with any weights that we add to the copper list. So we need to change some initialization values here. We need to change the start Y position to something like, I don't know, 3C maybe. This speed value, we don't need to change that. And we should have a stop position somewhere in the frame loop. And there's our bottom check right there. I'm going to put that at... Actually, let's calculate that. We want the raster line to start at a little bit above the logo, let's say 6 pixels, so that the start Y position is 4C minus 6, and the stop position would then be 1 pixel below the lower edge of the logo, which is hex 4C plus logo height plus 1. This is just to make it dynamic. We just calculated it to hex 8F, so we could only have typed, we could have made it easy and just typed hex 90 here. But of course, if we moved the logo, then we'd have to adjust things. If we change the height of the logo, that is. So this is the bottom check, and then we have something here which is also the top position. Well, the first initialization up there was just the starting position, which was somewhere in the middle. This is the actual top check. Let's fix that ugly thing. And let's put this at the same as the initialization value, which was -6. Excuse me. It's all this tap water that I'm drinking. There we go. And perhaps you can visualize in your mind's eye what I will attempt to do with this later on. And you know what, let's just set the screen buffer pointers and move the sprite down and call it a day, and continue with the fancy stuff in the next episode. Okay, let's see. We need to move the sprite down. That's no use right now. We can't see it because we've set the display window stop to end at the bottom of the logo. As an interesting aside, the reason that the raster bar is visible below the logo despite the display window stop vertically is because we are setting the background color, and the background color is always available there for changing. After all, for the top and bottom borders, we didn't need to have any bitplanes on to set it to dark blue and light blue, and it's the same with the raster bar, of course. Just a clarification there. All right. Perhaps I've not explained it before, but what I did there was press Amiga 3, which I had set to this position with Amiga Shift 3 once upon a time, and this enables you to put bookmarks in your source. Many modern editors lack this, which I will never understand. They have some concocted thing where you type comments to put bookmarks and you have a drop down, or, well, let's just leave it at not being very useful. For the screen buffer bitplane pointers, we're just going to set one bitplane pointer for now, at least. Perhaps I will change my mind like a woman and add some bitplanes, but for now that's all we're going to do. And we know that we should these addresses are free for the raster bar to move inside, and it's free up to hex 8F, after which we can set our bitplane pointer. So let's put a weight in 8F07, and let's paste that and rename it to, well, logically enough, screen bitplane pointers, and leave them uninitialized. Well, actually, let's be lazy and just put the screen shifted down by 16. Well, let's not. Let's be good boys and make it dynamic. And we do this the same way as before. We, instead of loading effective address logo, we load effective address screen. We move it into D1, we swap it, we move it, and we haven't set the new poke pointer yet. So we need to do that, and we swap it and move it at a different offset, and that should set the screen buffer but not show anything yet, since we haven't changed the display window start and stop. Sorry, the display window stop vertically. I'm just going to check that I'm still recording. Yes, I was. Just checking that because I managed to fill my C: hard disk the other day and kept on talking for another 30 minutes. And I had to do it all over again. So we have bitplane pointers for the screen buffer. So all we need to do is change the display window stop vertically, and so we need to replace this with something like this that we had before. And as you can see, well, how interesting! I must be disabling some bitplanes. If you've written exactly what I've written so far in the tutorial, you've made your first demo effect. Isn't that cool? Maybe we should just put a little space between us and the bottom limit of the raster bar movement there. And now I'll move this bookmark to here. And for easy access, I'll just move it down a bit. Well, that worked better, but we need to turn off some bitplanes. Let's do that with a weight. Sorry about that. Well, sorta, kinda. What the hell? It seems to me that we haven't calculated the stop of the logo properly. We have, so what's the problem? I'll pause here, and of course it's easy to see why now. Because the raster bar is something like 5 pixels high, we have a number of weights here that surpass this 8F position, so that any weight that we have here will need to be 8F plus the height of the raster bar plus 1. So, because we need to turn the raster bar off as well. We should go ahead and restore the background color, by the way, to 667, like it was above the raster bar. We need to calculate hex 8F plus 6, 95. And this should take care of it. However, as you can see, the red stripes there that are 6 pixels high, we need to lose them somehow. We'll fix that later. And for now, we can see that we are displaying some strange things, and that's because we haven't reset the modulo to 0, and we haven't set the DDF start and stop properly for 320 pixels widescreen, which is what we want. So let's do that. And let's check that. As there you can see extra clearly the red stripes that we need to get rid of. Likely we'll just it will be simple to just set color 7 to the background color for now. That's a quick fix. Okay. Actually, you know what? I think I will well, I haven't worked out the effect yet properly, so we'll just have to save that for the next tutorial. And go ahead and set the number of bitplanes to 1 to get our random data back. There we go. So everything as it should be. We can decide on what to fill the screen buffer in the lower half of the screen with later, and what color it should have. And well, that's it for now, I think. Yep, I'm happy with this ending. We've made some progress. We've put the logo inside our demo, and we've adjusted the raster bar, and we have bitplane data from 2 different sources, the logo and the screen, being displayed with a sort of a split in the middle, you would call them for older 8-bit computers. With the copper, of course, it's every weight is a split, is a potential split. You can put weights effectively on every raster line on the screen and change any amount of registers you want. It is well, that's one of the reasons I at least love Amiga. Thanks for watching, and see you in the next episode.